Thank you. Good afternoon. My name is Simone Lucertini. Allow me to introduce myself because this work is a collaboration between the university and the industry. The reason is I am an industrial PhD student with the University of Perugia within the machine construction group, but also at the same time I work for an American company, which is Terex. We design and build self-propelled aerial working platform, like the one you see in these pictures in the central part of Italy, in Umbria. And my role is design engineer principal. Today we will focus on welded joints for steel structures subject to high cycle fatigue on complex welded structure. With complex, I mean where the welded joints have a complex geometry and also the numerosity of the joints is huge to analyze. We need an immediate industrial application tool, which is the requirement from the company side. Actually, the research develops a lot of innovative and very interesting methods that are giving very good results in terms of comparison to the reality. But actually, these methods are usually applied in very small scale and only by university usually. While for the industrial application, we still rely on consolidated methods like a nominal stress method or a hotspot method, which usually have a very huge application. They are required by regulations, but are very general and usually they require a lot of physical testings. We need to condense the two words in one single tool. So the objective, this work is it continues the work we prepared last year when we developed the idea to use basically the structural stresses derived from nodal loads from shell elements in FE analysis to predict the strain energy density, which is a very complicated quantity. Actually, we improved the theoretical background and its robustness. We added some features and we tested different scenarios I will show to you. And we are developing an applicative tool for direct industrial application. And we hope to deploy all of this work as an open source library in the next future. So today we are going to revise the reference theory. I'll present you the method and we'll make some energy considerations. And then I present the application part, so the tool, its performances, and the future next steps. Why are we using shells to model a structure? Because we want to model complex structures, very big and entire machines or all the components of a machine. And the shell model can be used to make a quick static structural assessment, including also deflection analysis and stiffness analysis. We can do a quick model analysis on the structure, and also a simple shell model can be used in dynamic multi-body software like Adams, for example, to predict the dynamic loads. But actually, the fatigue is never considered at the beginning of the design stage, only at the end. We want to include this at the early design stage phase of a project. So these methods have the aim to give information about fatigue since the beginning, since your first design. Actually, the average strain energy density method is well known for the academic research, and it's based to retrieve the strain energy on a small volume at the, this is a welded joint, on the weld toe, basically. The radius depends on the material, and it can be done through FEA, but it requires a very fine mesh and some detail analysis. So by retrieving this strain energy density value, we can predict the static and fatigue failure of the component. This method shows to be very accurate. It has been proven through numerous tests and publications, but is slow to apply in the real application in the industrial reality. And its output is an energy, a quantity that engineers don't want to manage usually. As opposite, there is an interesting method that is used in automotive, which derives the stresses from the nodal loads on a shell model. So for example, a T-joint, a welded T-joint is modeled like this picture with shell elements, simplified shell elements. We want to know the stress on the weld toe, on the weld path, but we don't use the stress from the mesh element directly, but from its nodal loads. For loads, I mean forces and moments in all the directions. So retrieving the nodal loads, combining them together, and basically distributing through the element edge and by its length, we derive a distributed load that turns out that this load basically can allow us to calculate. It's not that in our application at the middle of the node. In the literature, you will find different approaches calculating at the nodes, but the result is the same. But we can calculate a simplified stress, which turns out to be mesh insensitive. So if you change the mesh size, more or less, the value of the stress is the same. So it's a new, unique way to retrieve the stress. And the stress is can be viewed as a combination of normal stress and bending stress. So also very easy to understand for engineers. This is industrially accepted, that it's a different formulation. It's included in some software like Encode or FESafe, but it has usually a lack of precision. We're trying to merge now the two presented methods together. So we ask, can we predict the strain energy density in a 3D complex model, FEA model, on this small control volume by means of this super simple model made just few shell elements, super simplified. The key concept, of course, is to firstly convert the stress we can retrieve from this simplified model to an energy quantity, but of course we need a compensation parameter because there's no information on the average strain energy density in this model at all. So we need something to compare those two results. And this can be done only in post-processing, so you just need to resolve the simplified FEA analysis also with a unitary load, and then our tool, which is written in Python, can extract the nodal loads, rescale your real load if necessary, calculate the structural stresses, then predict the strain energy density, and then going for the proof of strength static or for fatigue. That's the core. This compensation parameter depends mostly on the thickness of the plates you're going to join. So in this example, from 2.5 to 6 mm of thickness, which is the range required by the company needs, basically. And this was the calibration curve. So the solid one is the reference, so is the full model, 3D model enhances with solid elements, a lot of them, so it's a complex FEA model, while the dashed line is our estimation just using a super simplified shell model. And you can see for all the path here, of course the energy is not constant, but we are following perfectly the shape for all, basically for all the value of thickness. So the method is promising. What happens if we completely change now the shape? So instead of the T-joint used for calibration, we apply to an hollow section, a tube here. And the loading conditions are completely different. So you have the full model, you will need to apply this method really. So you have CAD preprocessing and then complex meshing to grant you achieve the correct values for the energy and convergence, versus our super simplified model, few shell elements, super simple and super fast. Again, the results are very close. The compensation parameter is the one found in calibration. We didn't change it. So we find a very good correlation still. The global error, just to give you a number, is under 8%, which is a good result for a super simplified model. And remember that actually we changed the shape of the joint completely. We changed the loading type and loading direction, and we make different generally boundary conditions. So the model is completely different. Why? It is possible to predict the strain energy density just using this simplified stress. We went to analyzing in detail the energy of the mesh elements for solids. you know this equation for linear elastic strain energy. And basically, you know, the stress vector and the strain vector are connected by the matrix D, which contains information about the material, linear elastic material. And then we know how to connect the nodal displacement with the strain of the element. So in post-process, we created a Python tool to calculate the energy on our own. We used, to simplify, an X8 solid element, isoparametric formulation, and full integration with eight Gauss point, typical. So those are the shift function of these mesh elements. So we are now able, in post-process, to gather from ANSYS, in our case, the nodal location and the nodal displacement, and calculate the energy, the strain energy on our own. We did it in two ways. One, considering only the strain vector, and one time only the stress vector to understand the difference. Of course, the sum will be the same. But we wanted to analyze the components. So we did a lot of tests basically by using all the vector or eliminating all but one just to see the dependencies. And we found interesting this one with the stress, because here the results on the well path, this is the halfway to this path. I will show the results. So the dash red line is the ANSYS results. ANSYS can give you only the full energy, so considering the entire stress vector. And our prediction for the full energy is the blue line. They are perfectly the same. This and here are 5%, so the error here is 0.1% between our calculation and ANSYS one, just to understand that we are calculating well the energy. And what happens if we choose only to consider this component of the stress and put zero the others? And basically we have the green curve, which is the entire energy of the system. And it's this stress component is the one we get from the nodal loads. That's the reason we can predict the strain energy density. Here we have the other components, so the tension in Y and Z direction, or all the tau together, okay? But you see their contribution is very low compared. In the applicative way, we develop a tool to gather information in our need directly from an ANSYS RST files. We load it, we get the mesh, and we created a system to classify the mesh elements automatically. So the gray elements are removed from the analysis. The yellow elements are recognized as well-beat elements, and the blue elements are the well-to elements where we extract the nodal loads and the thickness automatically, of course. This system can also detect open and closed path. And the application is immediate, so the system calculates the nodal loads, the stresses, and can predict the quantity like the stress, and plot in 3D using free open source tools. But we can also map our prediction of the strain energy density over all the geometry. And of course, we can also plot them in a simple 2D plot, immediately in multiple weldments of an entire structure. You can see which are the worst cases and where you can have a failure. This can be applied to complex structure. This is just a portion. Imagine an entire machine is made of 10, 20 parts like this. So we super simplify the modeling. This solution in ANSYS could take minutes, and our tool, again, another minute to solve it, to estimate the strain energy density. Let's say in 5 minutes, basically, you can run the FE analysis and our post-processing. And immediately, the engineer can have a visualization of what's going on in terms of also fatigue prediction, see which are the worst places where in future the engineer can concentrate or change the design immediately, see the things are not going well, so I change the shape of the entire element, or I do refinement more accurate with complex 3D model, but only in a small part. Just to give you some numbers for those two elements in comparison, the meshing time between solid and shell model decreased by 15 times. Meshing this one for the energy density is leads you to millions of elements just for a simple joint, imagine for a complex structure. And the solution time is at least 5 times faster, just to give you quick numbers. So this method, in conclusion, can estimate a complex quantity like the strain energy density by means of a simple representation. And remember, this thing is important. If you have a solid model, if you change the thickness of the plates, you have to change the CAD model, remesh, and rerun the analysis. Actually, our model is the same. For all the thicknesses, you model with just the shells and change analytically the parameter. And this allows a fast evaluation of static and fatigue strength since the early design stage, which was our goal. For an industrial standpoint, allows fast iteration over multiple solutions, and it allows immediate individuation of critical areas where you need to go in more deep investigation. Just very quickly, so in the next future, we are planning to improve this method and make it directly applicable and more easy to use. Thank you.